Right now, at this exact millisecond, there are over 500,000 people suspended 6 miles above the Earth. To understand how that trust was earned, you have to look at the fragile origins of early aviation. It began as an experiment of canvas and exposed wood, heavily dependent on the manual guesswork of draftsmen. This illustrates the safety factor, dictating how much stronger a part must be compared to its expected load. Positioned above the baseline survival limit is the over-engineered Boeing threshold. When severe aerodynamic stress hits the airframe, this mathematical gap absorbs a violence before structural failure. That specific mathematical rigor was then scaled across massive factory floors. Every single aircraft structure rolling off the line had to meet the exact same punishing threshold. As aviation advanced from open cockpits to highly complex, pressurized metal machines operating in the upper atmosphere, enforcing those tolerances became exponentially more difficult, but it remained completely mandatory. The Boeing engineering standard operated as a mathematical formula designed to systematically calculate human doubt out of the mechanical equation. In the modern jet age, an aircraft fuselage is subjected to brutal tearing forces and extreme pressurization cycles. Sealing human lungs safely inside requires near perfection. The company achieved that perfection through automated, unyielding precision. They forged raw aluminum into massive, seamless pressure vessels capable of withstanding the violent forces of the stratosphere. But the true test of this engineering wasn't whether a passenger felt safe, it was whether the professional operator did. Pilots are the ones who actually understand the physics threatening to rip the plane apart. Every time they sit in the cockpit, they stake their own lives on the absolute integrity of those systems. Decades of surviving those stakes birthed an internal, industry-wide seal of approval. The operators themselves adopted a universal phrase: "If it's not Boeing, I'm not going." For decades, that phrase meant that Boeing's internal quality controls had become the gold standard for the entire industry, the final word in airframe integrity. Today, a sprawling, interconnected global infrastructure operates continuously, moving millions of people and billions of dollars in cargo on top of that engineered baseline. Beyond the delivery of physical aircraft, Boeing's operation generated a steady supply of industrial confidence that allowed this global network to take root. That manufactured confidence serves as the foundational scaffolding for modern global trade, for international travel, and the broader economy. Yet this social contract remains incredibly fragile. It operates as a binary system. It only functions as long as the underlying engineering is entirely uncompromised. When a singular entity writes the terms for human survival at 30,000 feet, any deviation from absolute mathematical rigor represents a direct breach of the social contract itself. At 16,000 feet, a door plug ripped away from an Alaska Airlines Boeing 737 MAX 9, exposing passengers to the open sky. The physical breach translated instantly to the financial markets. Investors reacted to the safety failure by dumping shares, stripping billions in valuation from the company in a matter of days. Regulators grounded the fleet, and lawmakers issued subpoenas. Boeing's leadership was forced into wood-paneled hearing rooms to answer for a growing list of systemic failures. The immediate fallout cost the company more than just lost contracts. It evaporated a significant portion of its total market value. These events represent a fundamental break in the public's trust. They mark the moment a global leader in aviation lost its standing as the final word on flight safety. For decades, Boeing was the global standard for precision engineering. Its culture was defined by the rigorous demands of aerospace physics. A company with this much institutional knowledge doesn't forget how to build a safe airplane, yet the physical integrity of their machines began to fracture. To understand why, we have to look past the hangar floor and into a series of specific management decisions that changed the company's internal priorities. The danger didn't start with a mechanical fluke in the air. It began with a set of financial mandates established on the ground. A new conflict emerged within the company: the hard requirements of aerospace engineering versus the quarterly expectations of Wall Street. Leadership moved away from a culture focused on technical perfection to one prioritized around optimizing the balance sheet. This shift led to the aggressive outsourcing of mission-critical components. Instead of building planes under one roof, the process was split among a network of third-party subcontractors. This physically separated the design engineers from the manufacturing teams. The people responsible for the blueprints were no longer in the same building as the people turning the wrenches. This separation created communication gaps and weakened the oversight that had historically caught errors before they reached the runway. Executives focused on a metric called financial optimization, a goal that prioritized reducing immediate overhead to boost the stock price. Under this pressure, meeting production deadlines became more important than stopping the line to address assembly defects. This chart illustrates the cost. As the green profit line moves up, the blue safety tolerance line steadily declines. When that blue line crosses into the red, the safety buffer is gone, trading long-term reliability for short-term gain. This meant that financial targets were effectively overriding the technical warnings coming from the factory floor. Management didn't actually eliminate the cost of quality control. They simply deferred it, creating a physical debt that would eventually have to be paid. Today, that debt is visible in long rows of grounded fleets and a crippled production schedule. The savings gained from outsourcing have been completely wiped out by the billions lost in repairs, legal fees, and a permanent drop in market share. Boeing is now attempting an emergency reorganization, aiming to stabilize its manufacturing and regain its certifications by 2026. Success depends on a total reversal of the last 2 decades, putting technical expertise back at the center of the company's decision-making process. The history of the company shows that when financial extraction replaces engineering as the primary goal, the product eventually fails. You can use a spreadsheet to make a balance sheet look perfect, but a spreadsheet cannot change the laws of physics. Look at the Boeing 747. When it rolled out in the late 1960s, it was an absolute leviathan, dwarfing anything else in the sky. But building this mammoth machine required a financial bet so massive it nearly bankrupted the entire company. A conventional accounting department would have looked at the existential risk on the ledger and killed the project immediately. Boeing, however, ignored standard corporate logic. They viewed the accounting department as a necessary evil whose only real job was to buy their aluminum. To understand why a corporation would risk total ruin for a single airplane, you have to look at the fanatical, almost religious culture that actually built it. That culture was forged decades earlier. The company was founded in the rugged, rain-slicked industrial yards of 1916 Seattle. William Boeing established a rigid environment where engineering was elevated to an absolute devotion. Inside these drafting rooms, the company was run by an elite hierarchy that insiders called the Association of Divine Engineers. These men wore slide rules on their belts. The intricate mathematical scales etched into this tool were their primary source of truth. In this environment, status was earned through the mathematical perfection of wing load calculations. Inside Boeing, corporate authority came from mechanical truth. This diagram illustrates their golden rule: inherent redundancy. If a primary hydraulic system fails, halting operations, a secondary backup automatically takes over. If that backup also fails, a third analog physical cable bypasses the electronics entirely. You can see how this philosophy dictated the physical assembly of the aircraft. Deep inside the metal skeletons of these fuselages, miles of redundant cables and hydraulic lines were meticulously layered over each other. Removing all physical risk was the singular objective, regardless of the extra weight, time, or cost added to the final product. Inherent redundancy was an ironclad belief system. To these engineers, failure in the air was simply unacceptable. Fast forward back to the late 1960s, and that uncompromising engineering culture collided head-on with the massive scale of the 747. Scaling up those triple redundant safety systems created a paradox. To guarantee zero physical risk in the air, Boeing accepted maximum financial risk on the ground. The engineers pushed the project forward anyway. They were willing to face bankruptcy because the integrity of the machine held more value to them than the company's profit margins. Making just one of these planes was immensely complex, but they needed to integrate entire fleets into busy terminals around the world. Achieving this level of structural innovation required a culture completely detached from conventional financial caution. Boeing's golden era proved that fanatical engineering could outperform corporate profit targets. These massive machines emerged directly from an uncompromising, almost religious cult of math, a culture that completely ignored everything except for absolute physical reliability. By prioritizing physical truth over financial survival, these engineers built the safety record that made the era of mass travel a routine reality. Prior to 1997, Boeing's identity was defined by the Seattle assembly floor. Notice how the engineering stations are built directly into the space, alongside the mechanics. At this scale, technical precision was the primary metric of success. A single engineer had the authority to stop the entire assembly line to address a technical flaw. However, this level of high-precision engineering is expensive. By the mid-90s, the company struggled to maintain its high R&D costs while competing against the lean margins of global rivals. In 1997, Boeing acquired its struggling defense rival, McDonnell Douglas. To the public, it appeared Boeing simply consolidated its lead by absorbing a competitor. While Boeing was the buyer, the leadership structure of the smaller firm began to spread through the larger organization. On paper, the transaction was straightforward. Boeing absorbed McDonnell Douglas to consolidate market share. In the following years, executives from the acquired firm filled key vacancies in Boeing's upper management. These new leaders were trained in finance rather than aeronautical engineering. They focused on immediate cost reduction and stock performance, moving away from the long-term investment cycles required for aircraft development. For the engineers in Seattle, the daily work of assembly continued, even as the priorities at the top of the company changed. This acquisition meant that for the first time, Boeing's direction was set by a group focused on the balance sheet rather than the flight deck. Management soon moved to separate the corporate office from the manufacturing plants. In 2001, the headquarters moved to a skyscraper in Chicago, 2,000 miles away from the nearest factory floor. This distance meant people making budget decisions no longer interacted with the staff building the planes. Physical separation made it easier to treat aircraft production as a series of financial data points. A later move took the executive team even further east to Arlington, Virginia. This placed the company's leadership closer to political lobbyists and regulators than its own technical experts. By increasing the miles between the boardroom and the product, management reduced the influence of the engineering staff. Back in the factories, the results of this corporate shift became visible. Management introduced performance metrics that prioritized the speed of delivery and the reduction of overhead. The stock market responded positively to these efficiencies. Billions of dollars were used for stock buybacks to increase share prices, rather than being spent on researching new safety systems or aircraft designs. On the manufacturing floor, this pressure led to accelerated timelines. Internal warnings about quality were frequently dismissed as obstacles to meeting quarterly production targets. The priorities that defined Boeing for decades had been replaced. In this environment, the financial health of the stock took precedence over the technical integrity of the aircraft. Modern commercial aviation is dominated by the speed of corporate financial optimization, forcing a fierce global duopoly between two giants, Boeing and Airbus. Then, in the early 2010s, Airbus blindsided the market. They introduced a new, hyper-efficient jetliner capable of massive cost reductions. Fuel is an airline's single biggest operating expense. Because the new Airbus models promised airlines millions of dollars in continuous fuel savings, industry loyalty shifted almost overnight. Boeing's grip on the market broke. A competitor had finally optimized for the only metric that mattered to airlines, the bottom line. Inside Boeing headquarters, executives scrambled to mount a response to the sudden threat. The engineering response was straightforward: design and build a brand new, modern airplane from scratch. This chart highlights the friction point of that plan. A ground-up redesign would take a full decade of engineering and cost $15 billion. Boeing's corporate culture refused to tolerate that kind of expenditure in time and capital. Instead, executives demanded a shortcut. They mandated that the massive, fuel-efficient new engines be slapped onto their 50-year-old existing airframe, the 737. Prioritizing an immediate cost-saving patch over a long-term engineering solution set a physical trap for the design team. Down on the assembly floor, the mandate from the boardroom immediately hit a physical wall. The legacy 737 was built in the 1960s to sit low to the ground. This allowed passengers to board from the tarmac using simple folding stairs. The new LEAP engines achieved their fuel efficiency through size, featuring a diameter much larger than the engines the 737 was designed for. This schematic wireframe compares those two variables. You have the tight underwing clearance of the legacy 737 competing for space with the oversized diameter of the new engine. If you attempt a standard mount, the new engines physically intersect with the tarmac. The engineering team was trapped by the rigid geometry of a half-century-old design. You cannot force modern hardware into a legacy spatial footprint without breaking something. This posed a central engineering dilemma. How do you attach an engine to a wing when it physically does not fit underneath it? This side profile vector shows the structural workaround. To clear the ground, engineers mounted the engines higher and further forward on the wing. Relocating thousands of pounds of weight and thrust over the leading edge completely rewrote the aircraft's pitch and stability. Ultimately, by solving a localized spatial problem, the engineers had altered the physical balance of the entire aircraft. Initially, the workaround seemed successful. The plane was built, the engines cleared the tarmac, and the financial crisis appeared to be averted. But the compromised geometry would be tested to its limits under a specific flight condition: steep, high-thrust climbing. This aerodynamic profile illustrates the problem. Thrust generated further forward acts like a lever. Under high thrust, this leverage pushes the nose upward aggressively. This extreme pitch risks an aerodynamic stall. The wings lose lift, and the plane drops. In the desperate quest to optimize a balance sheet, Boeing overrode the laws of aerodynamics, resulting in a historically safe airframe that now contained a fatal stall risk. For nearly a century, commercial aviation had one true north: Boeing. They built their name on obsessive precision, turning out complex machines so reliable that "if it ain't Boeing, I ain't going" became an industry mantra. Then came the new 737 MAX. Within 5 months, 2 aircraft fell from the sky. October 2018, Lion Air. March 2019, Ethiopian Airlines. 346 people died in those crashes. The flight data showed both planes entered violent, unrecoverable nosedives, actively fighting the pilots all the way to the ground. The aviation world hit the brakes. Regulators ordered the immediate grounding of every 737 MAX on Earth, leaving billions of dollars of hardware parked in the desert for 20 months. How does a company built on a culture of safety engineer an airplane that actively forces itself into the Earth? The answer comes down to a quiet choice made in a boardroom. Because of its larger engines, the new 737 MAX had an aerodynamic quirk. Physics naturally forced the nose to pitch up too high. Redesigning the airframe would cost billions. Instead, Boeing opted for a software patch, installing code called the Maneuvering Characteristics Augmentation System, or MCAS. The programming was straightforward. If the plane sensed the nose creeping toward a dangerous angle, the software quietly stepped in and pushed the nose back down, masking the aerodynamic flaw entirely. Boeing had reached a pivot point, no longer relying on physical design for stability, but on digital commands to override the plane's natural flight behavior. This highlights the system's fatal compromise. All the authority granted to MCAS relied entirely on data fed from a single external sensor on the nose of the plane. Aviation engineering relies on redundancy. Relying on one sensor means if a bird strike or freezing rain damages that one little probe, the flight computer starts reacting to a false reality. Normally, a system this powerful requires pilots to undergo extensive retraining in a simulator, but airlines avoid retraining whenever possible. It takes pilots out of the air and costs massive amounts of money. To market the MAX as a cheaper option that required zero simulator time, Boeing made a calculated decision. They simply didn't tell the pilots that MCAS existed. They built software capable of overpowering the crew, tied its activation to a single fragile sensor, and kept it a total secret to protect their sales margins. Put yourself in the cockpit of Lion Air Flight 610 or Ethiopian Airlines Flight 302. The crews were fully certified, flying a brand new aircraft from the world's most trusted manufacturer. Shortly after takeoff, that single external sensor failed. It said corrupted data into the flight computer, falsely reporting that the nose was pitched dangerously high. Obeying its programming, MCAS woke up. It began aggressively and violently forcing the nose of the plane down toward the ground. The pilots pulled back on the controls with all their strength, but because the system had been scrubbed from the manuals, they had no idea what they were fighting or how to turn it off. This tragedy was the direct consequence of the specific compromises made during the plane's development, the result of choosing profit margins over redundant safety systems. The decision to use a secret software fix to hide a physical flaw didn't just lead to a global grounding, it ended Boeing's era as the undisputed gold standard of aviation engineering. In January 2024, a brand new Boeing 737 MAX 9 commercial passenger jet began its initial climb out of Portland, Oregon. Upon reaching an altitude of 16,000 feet, a structural door plug separated from the fuselage and was pulled into the atmosphere. Inside the passenger cabin, the resulting explosive decompression was immediate, a sudden roar of freezing wind and a drastic drop in oxygen. Modern aviation failures are typically associated with complex software glitches or sensor errors, digital bugs that are difficult for the human eye to detect. But the federal investigation into this blowout immediately pivoted away from computer code. They were looking for a physical, mechanical cause. The investigation revealed that the plane had left Boeing's factory with the 4 critical alignment bolts required to hold the door secure completely missing. This specific failure changes the nature of the conversation. This was not a sophisticated technological glitch, but a collapse of basic manual assembly line discipline. To understand how a component simply disappears, you have to look at the scale of the aircraft manufacturing floor. Assembling a multi-million-dollar jet requires thousands of precise human actions. Mechanics drill, rivet, and secure parts by hand across miles of scaffolding. The process relies on quality inspectors. They serve as the designated failsafe, specifically employed to catch simple human errors, like a missing bolt. A single mechanic skipping a step is an individual mistake, but a missing structural component slipping past inspection entirely suggests that the safety net itself has been compromised. That safety net was strained by an opposing force, the relentless demand for quarterly production speed. Financial delivery targets began to carry more weight in the factory's rhythm than the physical engineering requirements of the aircraft. This chart shows the conflict at play. As production quotas push the speed line higher, the time allowed for thorough safety inspections drops. At this point, the demand for output overrides the safety baseline, shifting behavior on the factory floor. Quality inspectors who flagged defects were increasingly viewed as obstacles to hitting those delivery numbers. Instead of stopping the line to correct problems, management routinely ignored or reprimanded the very people hired to find them. Bypassing the failsafe to avoid missing a delivery date became an intentional, systemic choice. The factory floor had moved away from optimizing for safe airplanes, focusing instead on meeting on-time financial metrics. Previous aviation groundings were intended to serve as a definitive wake-up call for the manufacturer, but the financial pressure for speed was too deeply entrenched in the daily operations for those warnings to take hold. The missing bolts on the Alaska Airlines flight are the physical manifestation of a production line where speed had outpaced safety. If a system is broken enough to skip securing a primary exterior door, it raises questions about every other component on the aircraft. A highly advanced aerospace company failed at the absolute simplest task of using a wrench. An airplane is only as secure as the corporate culture that builds it. When financial targets dictate the pace of the assembly line, The safeguards meant to prevent failure are the first thing to be discarded. For decades, the name Boeing stood as the primary symbol of American industrial might. This was a titan defined by undisputed market dominance and a century-long legacy of moving human travel forward across oceans and continents. But a corporation of this scale doesn't operate as a single solid block. It functions like a complex machine, relying on an array of independent subsystems, from commercial jet manufacturing to defense and space exploration, to maintain its massive structure. Because of that architecture, an empire like this rarely collapses from a single error. Instead, the danger comes from compounding failures, where every load-bearing pillar begins to buckle at once. The first major fracture appeared in the company's terrestrial core. Its commercial aviation division was actively bleeding out. Quality control scandals and grounded fleets drained cash reserves and eroded public trust, placing immense financial and reputational pressure on every other division to compensate for the losses. To maintain its standing, leadership needed a high-profile win. All hopes for salvaging the company's prestige shifted upward, resting directly on the shoulders of its highly respected space division. To offset the severe bleeding on the ground, Boeing required its next orbital mission to be a flawless, historic victory. That victory was supposed to be Starliner. This spacecraft was designed for a prestigious mission, ferrying NASA astronauts to the International Space Station. But shortly after the capsule reached orbit, the hardware suffered sudden mechanical breakdowns. Specifically, the vehicle experienced multiple failures within the array of thrusters required to maneuver the craft. Those thruster issues were compounded by secondary faults. The orbital systems began leaking helium, a gas used to pressurize the propulsion lines, and the leaks were spreading through the spacecraft. Ground control and the station crew were forced into immediate technical triage, scrambling to diagnose the cascading faults while the astronauts waited in orbit. Instead of delivering a public relations triumph, the Space Division had manufactured a highly visible crisis. After weeks of analysis, NASA delivered a devastating safety assessment. The agency concluded that the hardware was too risky to fly its own astronauts home. Rather than gamble on the compromised Starliner, NASA elected to leave the crew on the station for months rather than risk the return flight. Then came the ultimate corporate humiliation. To rescue the crew, NASA turned to Boeing's primary competitor, SpaceX. While Boeing's multi-billion-dollar capsule sat crippled in orbit, a younger commercial disruptor was executing the very flights the legacy giant could not. This public defeat stripped away Boeing's reputation for engineering supremacy, marking the moment the former monopoly was beaten in its most prestigious arena. By late 2024, the technical failures in orbit were being mirrored by a complete breakdown of operations on the ground. Tens of thousands of union machinists walked off the job, launching a massive strike that targeted the already weakened corporation. The logistical consequence was immediate. Assembly lines went dark, and the company's core manufacturing and production effectively froze. An aerospace manufacturer already losing billions from its grounded jets and failing space contracts cannot withstand the total shutdown of its labor force. This chart shows compounding financial losses. As layers for commercial, space, and labor strikes are added, the company hemorrhages billions. Wall Street's immediate reaction pushed the company's credit rating precariously close to junk status. When commercial losses, technical failures, and labor unrest converge, they create a systemic pressure that no single pillar of the company can support. By the end of 2024, the former monopoly ended the year as a company fighting for its life, hovering on the absolute edge of insolvency. When these massive engines roar to life, they power a critical pillar of national security infrastructure. Boeing provides the mechanical weight that supports global logistics and military readiness. Its aircraft form the physical backbone of international travel. When a manufacturer reaches this level of integration into global systems, it functions as an empire that cannot be allowed to fail. Yet this indispensable empire found itself facing the very real threat of total collapse. A structural failure at this scale threatens the safety and stability of the broader national system, reaching far beyond the company's own balance sheet. The root cause of this paralysis was a problem of geography. Leadership was attempting to manage a highly complex physical manufacturing process from corporate offices positioned in Virginia, half a continent away from the factory. That geographic distance bred a bloated corporate bureaucracy. Decisions were made in a vacuum, entirely removed from the actual aircraft built on the floor. To execute a radical reconstruction, Boeing brought in an outsider, aerospace industry veteran Kelly Ortberg. Ortberg's background distinguished him from the typical spreadsheet-driven executive. He is a mechanical engineer. Fixing a broken physical machine requires a diagnostic mindset, one that prioritizes mechanical reality over standard corporate restructuring. Ortberg recognized immediately that it is impossible to fix a factory floor from an office 3,000 miles away. His very first move was to abandon the Virginia corporate suites and relocate his own office directly back to Seattle. He placed himself within literal walking distance of the manufacturing floor. From there, he began dismantling the sprawling layers of management that had traditionally isolated the product from the leadership. To fill the resulting power vacuum, he placed veteran aviation engineers back at the helm of the company's core operations. Forcing executives and engineers back onto the shop floor removed the buffer between leadership and the daily mechanical challenges of production. The final phase of this proximity strategy was the most drastic, and it was directed at the ground floor. Ortberg granted factory workers the absolute authority to halt the entire assembly line at any moment. If a worker spots a physical defect, they no longer need permission to pull the cord. This contrasts with the previous era, where quality control decisions were bottlenecked in a distant boardroom, far removed from the immediate reality of the line. Transferring operational power to the lowest rung of the hierarchy acts as the ultimate safety failsafe for the corporation. The corporate architecture has been rebuilt to revolve around the hangar rather than the boardroom. Boeing is moving away from a sprawling bureaucracy and toward a hyper-localized manufacturing operation led by engineers. When you build life-critical machines that keep thousands of people alive daily, the technical reality of the product must dictate the culture. True quality control and safety cannot exist where there is a vast spatial distance between leadership and labor. A company's ultimate safety mechanism isn't an executive policy. It is the proximity and empowerment of the workers who actually turn the wrenches. A few short years ago, the undisputed titan of American aviation was in a freefall, staring directly at bankruptcy. This chart tracks Boeing's market valuation, showing the moment the stock price plummeted below the $170 support line. Regulators circled the company, handing down billions in fines and penalties as the internal chaos became public. The financial fallout paled in comparison to the human cost, hundreds of lives lost to preventable engineering failures. The mechanics on the factory floor hadn't forgotten how to build an aircraft. The breakdown happened because executive leadership changed the entire incentive structure behind the assembly line. Boeing traded the rigorous, life-saving pride of its engineering teams for the temporary approval of financial markets, making disaster inevitable. Leadership replaced mechanical engineering with a different discipline, financial engineering. Instead of funding the decade-long research required for new airframes, executives prioritized massive stock buybacks to satisfy Wall Street's demands. You can massage a spreadsheet to make a quarter look profitable, but the physical laws of aerodynamics and metallurgy cannot be cheated. The moment an industrial giant manages its blueprint solely to please shareholders, its destruction becomes a mathematical certainty. This obsession with profit margins dictated exactly how the aircraft were physically manufactured. To strip away overhead, Boeing dismantled its internal supply chain and outsourced the production of critical components to external vendors. Whole sections of the airplane, like these massive fuselage components, were being constructed by Spirit Aerosystems, far outside Boeing's direct control. Handing off the physical construction meant handing off the oversight. Crucial quality control checks were moved away from Boeing's own engineering teams. Executives in distant offices were making cost-cutting decisions that actively compromised the integrity of the hardware on the floor. Outsourcing effectively severed the corporate leadership from the physical reality of the product they were selling. As the crisis peaked, the board realized they couldn't calculate their way out of a physics crisis. Boeing reversed course, spending billions to reacquire Spirit Aerosystems and bring the entire manufacturing process back in-house. This forced quality control and structural stabilization back under their own roof. The company moved its executives out of corporate suites and directly to the factory floor, placing leadership back in constant proximity to the aircraft hardware. Survival required Boeing to abandon the balance sheet and restore the link between the decision-makers and the machine itself. By mid-2026, the friction of this massive cultural pivot finally began to yield results. After years of internal resistance to the reorganization, the engineering-first focus translated into hard structural stabilization. This graph shows the market's response, with the stock price stabilizing consistently above $225 per share. Global airlines responded to the operational overhaul. At a recent economic summit, Boeing secured a historic commitment for 200 next-generation aircraft. This rebound was the result of a grueling return to the assembly line, where meticulous craftsmanship, not stock manipulation, finally restored market value. Financial stability and Wall Street approval are downstream effects of prioritizing engineering excellence. Boeing's multi-year journey serves as a warning for the global industrial landscape. You cannot cheat the hard laws of physics with a share repurchase program. Boeing had to do more than patch technical flaws. They had to dismantle a decade of executive insulation and physically reintegrate every step of their assembly process. As the latest 777X ascends into the sky, it marks the definitive return of a company that has finally leveled out. Long-term survival in manufacturing is only guaranteed when the life-saving pride of the engineers comes first.
If you enjoyed this mini, subscribe right now so you don't miss the next one. Drop a like, share it with a friend, and comment your thoughts. What would you do? All right, subscribe, like, comment, and share. Thanks for being here.